Let's have a look at electrical safety and electrostatic discharge. Electrical safety is crucial for protecting both equipment and individuals from harm. One key aspect is managing static electricity, which is caused by an imbalance of electric charges. When a person touches electronic devices and there's an existing charge imbalance, both the individual and the electronics may experience an equalizing discharge. This sudden leap of electricity can potentially damage electronic components. The other danger of electricity is high voltage. High voltage can cause burns and death. In tech support, just being careful should keep you safe from this. A lot of the time you won't come across high voltages unless you are working in a server room or with specialized equipment. To start with, I will have a quick look at how electricity works. For the A+ exam, in-depth knowledge of electricity isn't necessary, but a basic understanding can be beneficial for tech support roles. It's often helpful to conceptualize electricity in terms of water flow, as they share some behavioral similarities, making the principles easier to grasp. Electricity involves the movement of electrical charge, a fundamental physical process. Voltage, a key measurement in this context, is the electromotive force, defined as a potential difference between 2 points. To simplify, imagine 2 water tanks linked by a pipe. Imagine one water tank is full while the other is empty, resulting in a difference in pressure between the two. To increase this pressure, you would need to enlarge the tanks. Similarly, in the realm of electricity, electromotive force can be adjusted up or down. This variation in force is measured in volts, such as 12 plus volts. Ground represents 0, so the voltage difference from 0 is 12 volts. The concept of voltage can be a bit perplexing, especially when considering a battery with its positive and negative terminals. The difference in voltage, say 12 volts, refers to the difference in electrical potential between these two terminals, and not to an output of positive 12 volts or negative 12 volts from each terminal individually. The key takeaway here is that voltage, essentially, represents the potential difference between 2 points. If you're finding the concept of voltage challenging, don't be overly concerned. For tech support purposes, the primary concern is simply to match voltages correctly. Excessive voltage can lead to damage, while insufficient voltage usually means the electronics won't function properly. Fortunately, many connectors are designed to be keyed, minimizing the risk of mismatching voltages under normal circumstances. However, there are rare occurrences where mismatches can happen. Later in this video, I'll explore situations where this might occur and how to handle them. The next measure of electricity that you will come across is amps. This is a measurement of how much electrical current passes a point, for example, a point on a wire. In computing, we often see amps used as a measure of how many amps a device will require, or the maximum amps a cable will support. For example, a cable may be marked as 5 amps to indicate it can handle a maximum of 5 amps. To enhance our understanding of how voltage and amperage function, I have installed a measuring device between the two towers. This device will accurately gauge the flow of water through the pipe. Notice that when there is water flowing past the measuring device, the needle on the device will go up. As the water flow slows down, the needle will also go down until it reaches 0 as the flow stops. When the tanks are balanced, the water flow stops, which would be the equivalent of there being no voltage difference between the 2 points. No difference means there is no force to push electricity through the wire, and thus no amps. No voltage difference occurs when you switch the power off, or if you are using a battery, the battery goes flat or dead. Voltage is controlled by a power supply or your power connection. It is controlled so the same voltage will be supplied to the device. The next question is, how are the amps controlled? Essentially, a device takes the amps it needs. To draw an analogy, a device drawing amps is like an animal drinking water. The animal only takes the water it needs, just as the device only takes the amps that it needs. Thus, unlike voltage, extra amps generally don't damage electronics. Let's use this knowledge to see how we may apply it in computing. I have connected a USB voltage and amp reader to a computer. It also measures watts, which I will cover later in the video. You will notice the voltage is slightly over 5 volts. This will remain pretty consistent, which is typical for devices that provide power. A good power supply won't have many fluctuations in voltage and should remain pretty consistent even under load. Now I'm going to connect a solid-state drive to draw power. You'll notice an initial spike in amperage as the SSD powers up. During its startup phase, the SSD communicates with the operating system, in this case Windows, and carries out initial setup tasks. After completing these tasks, the amperage requirement will decrease as the SSD settles into the state where it requires less power. I will now copy some files to the SSD. Notice that the amps go up when data is being transferred to the device. You can see the device will draw amps when it needs them, and this will reduce when the device is idle. Voltage will fluctuate a bit, but always remains around 5 volts. In the context of USB devices, the USB controller is designed to limit the amperage that can be drawn, which can sometimes lead to issues. The term current is often used to describe the flow of amps through a circuit. Essentially, a high current indicates a higher amperage. Now let's examine scenarios where excessive current draw might occur and the potential problems that can arise from this. A circuit overload occurs when there is more demand for current than the circuit can handle. Essentially, the amps exceed the limit of what can be provided by the circuit. When this happens, there is extra heat generated in the circuits and the cables and a higher risk of fire. Although it is possible for a device to pull more current than the circuit can handle, this generally does not happen when a device is the only device on that circuit. There are a lot of standards for electricity that prevent a single device from doing that. If you find that a device is drawing too much current, there is probably something wrong with it. Later in the video, we will look at what to do if too much current is being drawn by a device. If you encounter issues related to current overload, it's likely due to a situation like this, something you'll probably face at least once in your IT career. This often happens when devices are continuously added, leading to a tangled mess of cables. Users frequently daisy-chain power strips, stacking them on top of one another, usually tucked away under tables. These jumbles typically result from each person passing the responsibility on to the next person who takes over the desk. The real question then becomes, will you address the chaotic cabling or leave it for someone else to handle? Let us know in the comments. Besides being messy, let's have a look at what problems this can cause. Other than device malfunction, a common cause of overloading a circuit is daisy-chaining devices to the same circuit. Generally, this is achieved by daisy-chaining multiple power strips together. Now let's consider that we add some devices to these power strips. These devices don't require a lot of current, thus don't draw much current. Since all the power strips end up going to the wall socket through the same cable, the maximum current will be at that point. More on why this is important later in the video. Now let's consider that we add some more devices, but this time, some of them use a lot of current. The current has increased, but not yet enough to cause problems. In this example, we have a high-performance computer with a graphics card that uses a lot of power. Less powerful computers, such as a basic office computer, use a lot less power. Now let's tidy the office up a bit by doing some vacuuming. Vacuums pull a lot of current, so this is enough to max out the circuit. For optimum safety and efficiency, it's advisable to connect high current devices to a single power point. Alternatively, if sharing a power source, it's best to limit it to just a few low current devices to prevent overloading and ensure stable power distribution. Now let's have a look at what happens when the circuit is overloaded. Fuses and circuit breakers protect your equipment from damage. Essentially, when a circuit is pulling too much current, which may be referred to as overcurrent, the electricity is switched off. Thus, if you are using a device like a computer, It will switch off and you will lose any unsaved data. Fuses and circuit breakers act as emergency stop mechanisms that cut off power to prevent damage. There are various ways this is implemented. For instance, a device might have an internal fuse, which in older models was typically a glass cylinder containing a thin wire. This wire, designed to heat up under excessive current, would break if the current became too high, thereby breaking the circuit. In such cases, the blown fuse would then need to be replaced to restore functionality. You don't tend to see glass fuses used so much nowadays. They have been replaced with resettable fuses. These come in different shapes and sizes, but basically have a material that expands when it gets hot, either reducing the current or stopping it. If the power is cut off with these fuses, they will reset themselves after a certain amount of time, thus don't need to be replaced. If you have one of these, you'll generally notice the device may not work at all for a minute or two after the fuse is tripped. If you find the fuse keeps tripping, there is probably something wrong with the device. Remember, the fuse is tripping to try and protect the device from damage. If the device is pulling too much current, there is probably a component in the device that is damaged. To protect your equipment, circuit breakers are also used. Nowadays, most power strips will have a circuit breaker in them. It is recommended that you always purchase a power strip with one of these circuit breakers in. In order to reset them, there is usually a little button on the end of the power strip. If you discover that none of the devices connected to the power strips are receiving power, it's likely that the circuit breaker in the power strip has been tripped. In your building, there will also be a circuit breaker. Older buildings may have circuit breakers made of a wire that will burn out if too much current is drawn, and you will need to replace the wire. Newer buildings will have switches that, when tripped, will go to the off position. To reset the circuit, you just need to switch it back to the on position. If you find that you put it in the on position and it immediately goes back to the off position, there is something on the circuit that is drawing too much current. Possibly some equipment is damaged. Hopefully your fuses or circuit breakers save your equipment from damage. If not, something else may get damaged. In the case of electronics, too much current can cause components in a circuit board to burn. Look for black burn marks, although sometimes these can be hard to see. If too much current is traveling through an electrical cable, you may see black soot around the plug. This is not a good thing, and you generally should replace your cables and get your power point checked. In modern buildings and equipment, circuit breakers should prevent anything bad from happening. In older buildings, the protection may not be as good, and you may see melted wires. When this occurs, the cables need to be replaced. So, let's have a look at how we would apply all this knowledge. In the real world, spread out the load of your devices. This is only a real concern if the load starts getting too high. If you have a computer with just a few devices, you will probably be okay. If, however, you have multiple computers and devices, you should look at sharing the load across different circuits. Using power strips is fine, just plug different power strips into different power points. If the load is very high, you may want to consider using different circuits. Not all power points are necessarily on the same circuit. Sometimes it is just a matter of running an extension cord to another power point, even one in the same room. If you are working for a company, they may have an electrician who can advise you or install additional power points on different circuits if required. Later in the video, I will look at ways to better determine how much electrical load is being used. The next thing we need to consider is matching volts. In most cases, it is just a matter of plugging the device in. Some devices will have a voltage switch on the back. Although not all power supplies will have this, if they do, it is important to make sure it is on the right setting. To change it, use a screwdriver and push the switch to the correct position. Don't be concerned if the voltage is not exact. For example, if your voltage is 120 and it says 115 volts. The truth is, the power coming from your mains supply is an average and fluctuates above and below what they say it is. Thus, a small difference is not a concern for higher voltages like mains power. At lower power levels, a small voltage makes more of a difference. Thus, I would not plug a 12-volt power supply into a 10-volt device. In this scenario, since I'm using 240 volts, I will revert to the original voltage setting. Setting the voltage switch incorrectly can have serious consequences. If I were to plug it in and turn on the power with the wrong setting, the components inside the power supply could potentially blow up, posing a risk of an electrical fire. Therefore, it's crucial to ensure that the voltage switch, if present, is correctly set before connecting the power cable. Modern power supplies do not have this switch, as they will sense the power coming in and adjust accordingly. The other case where you will have to match voltages is when using external power supplies. Let's consider an example of a network switch. When plugging devices in like this, it is always best to use the power supplies that came with the devices. However, in some cases, a power supply may be damaged or lost. In this case, it is possible to use another power supply. However, care must be taken when doing this so you don't damage the device. The initial step is to examine the device closely to determine its voltage and amperage requirements. Typically, this information is printed directly on the device or on a sticker attached to it, specifying both voltage and amps. If this information isn't readily visible, consulting the manufacturer's specifications online is a reliable alternative. Additionally, it's crucial to check for voltage polarity, which is also an important aspect of the device's power requirements. There should be a diagram on the device to indicate if the center pin and outside parts are positive or negative. This information specifies the polarity of the inner and outer parts of the power connector. For instance, in this example, the exterior is negative and the interior is positive. Reversing these polarities will most likely cause damage to the device. Similarly, using an incorrect voltage can also harm the device. Therefore, it is essential to ensure that both the voltage and polarity correctly match the device's specifications. To understand what to look for, I will look at the correct power supply for the device. On the power supply is the voltage output. In this example, it will be 7.5 volts and 1 amp. The amps need to be the same or higher. More amps should not cause a problem since the device will only draw what it needs, but don't increase the voltage as this can damage the device. The power supply will also have a diagram to indicate polarity. Make sure this matches the device that you are plugging it into. In some cases, if you lose your power supply, you may be able to find a similar one that will work with the device. If you don't have one, you can purchase a replacement or purchase a universal power supply. A universal power supply will have a number of different attachments, hopefully one of which will match your device and also be able to provide the required voltage output. It is always best to use the power supply provided by the manufacturer, but if that is not possible, a universal power supply is a good option. In a lot of cases, it will work. However, you may find in some cases it will not. Usually, with smaller electronic devices, there is a better chance it will work, but with larger devices like computers, universal power supplies don't always work. Now that we have an understanding of how electricity works and how to connect it, let's have a look at how we can start measuring how much electricity our devices are using. To understand what we are trying to achieve, let's consider two different examples. These are power being delivered at 240 volts at 5 amps and 120 volts at 10 amps. As you will see, in both cases, they deliver the same amount of power. For the exam and for tech support, you don't really need to understand the formula. This information is provided so you can get a better understanding of why we do things the way we do. Watts describes the rate of power flow and provides a measure of power regardless of what voltages and amps are used. It provides a common metric that we can use to compare power usage between different devices. In other words, we can use it to make an apples-to-apples comparison on how much power different devices are actually using. To understand this better, consider that the example of 120 volts has a certain amount of pushing power. Volts provides the pushing power to electrons, which is essentially another way of saying the power to push electricity through a wire. So the question is, if we double the volts, does this double the pushing power? The answer is, yes, it does. So when we double the pushing power, but halve the amps, this means the number of watts is the same. Thus, you can see how using watts removes the difficulty of working with voltages and amps, and gives us a simple measure to determine how much power a device uses. To understand why this is important, let's consider a computer power supply. If you consider this 500-watt power supply, it supplies a number of different voltages. Different devices inside the computer will use different voltages. Regardless of which voltages are used, the power supply will output a total number of watts. Thus, to work out if a power supply is powerful enough for the computer, we just need to add up all the watts used by the connected devices. Thus, counting the watts gives us a way to measure the total power required. You don't need to worry about what voltages or amps are being used. Thus, when purchasing a power supply, it needs to be equal to or greater than the total watts required. Since power supplies generally supply power a little under what they are rated for, it is generally a good idea to have a power supply rated a bit higher than what you need. Now that we have had a good look at how electricity works and how not to overload your circuits, let's have a look at the basics of how to keep yourself safe performing maintenance on computers. When performing maintenance on a computer, the first step is to shut down the device. Once this is done, switch off the power and unplug it. Some people do recommend just switching the power off and leaving it plugged in. This is to allow the device to be still grounded through the power cable. However, due to the risk of possible electrocution, we don't recommend this approach. Although switching off the power should prevent this from occurring, if something has gone wrong with the power switch, there is still a risk. Considering you may be fixing the computer because something has gone wrong, it is best to get in the habit of unplugging the computer. The next step is to hold down the power button. This helps drain any charge left in the computer. Computers can hold a charge even after being switched off. They generally only hold a charge for a few minutes at most, but some devices like monitors can hold charges for longer. I will look at some alternatives to grounding yourself later in the video. If you don't have any other anti-static equipment, the next step is to touch a metal part of the computer case. This will balance your static charge with the computer case. Nowadays, a lot of computer cases are painted, and touching them won't achieve anything. If this is the case, touch one of the screws. The screws have a thinner layer of paint, and thus you are more likely to make a connection and ground yourself. Make sure you don't touch any components. You essentially want to ground yourself. If you touch a component, you may damage the component if anti-static electricity jumps from you to that component. If there's no metal part of the computer case to ground yourself, find another metal object that is grounded. For instance, touching a door handle can help discharge any static electricity. When doing so, it's advisable to use your entire hand, as this increases the surface area in contact and reduces the likelihood of receiving an electric shock. Using just a small area, like a fingertip, increases the risk of experiencing a shock. Touching something grounded before touching the computer can prevent electrostatic electricity damaging components. However, once you are discharged of static electricity, you are still able to pick it up again. Thus, don't touch a door handle or something nowhere near the device you are working on, and expect not to pick up a charge when you are walking back to it. It is always best to touch a ground source that is near the computer you are working on so you don't pick up any charge before touching it again. Lastly, only replace components classified as field replaceable units, or FRUs. FRUs are elements like circuit boards, parts, assemblies, or devices that can be swiftly and effortlessly removed and replaced by a technician. These generally include components that are simple to unplug or secured with just a few retaining screws. Common examples of FRUs are memory modules, graphic cards, and CPUs, all of which can be easily removed and replaced by a skilled technician. Power supplies can also be replaced by a technician, but not any of the internal components. A good rule of thumb is that if a part can be removed simply by unscrewing, it's typically safe for swapping out during repairs. However, once you start dismantling covers and exposing circuit boards and internal components, it goes beyond the scope of basic technical work. Some components, like power supplies, can retain a charge and are hazardous to open. Even attempts to drain the power may not fully discharge the device. Therefore, it's strongly advised not to open such components or attempt repairs unless you have the necessary training and expertise. Let's have a closer look at static electricity so we can understand how to manage it better. The biggest danger of static electricity is what is called electrostatic discharge, or ESD. This occurs when there is an imbalance of electrical charge. An electrostatic discharge is the process of restoring the balance. As a child, you might have conducted experiments where your hair stood on end. This phenomenon occurs because your body accumulates a static charge, and when your hair gets near an object with an opposing charge, it reacts. Essentially, your hair is attempting to move toward the object to neutralize the charge imbalance. Let's examine this concept more closely. To understand the process better, consider that we have our IT technician. The IT technician has built up a static positive charge. Synthetic material creates and stores charge more than other materials. If you are working in an area where ESD is a very big concern, you may be required to wear cotton clothing. There is also special ESD footwear you can buy. Low humidity can also increase the amount of static electricity. Thus, you can see that just wearing different clothing and adjusting the air conditioner can decrease the risk of static electricity. So let's consider the technician is about to work on a computer component. This component is negatively charged, so when the technician touches the component, electricity jumps between them to achieve balance. Thus, when the IT technician touches the component, a small electrical transfer occurs, balancing the charge between the two. This sudden jump of electricity between the two can damage components. Modern components are generally more resistant to electrostatic damage, but that doesn't mean they are completely immune to static electricity. Some components remain more susceptible than others. Let's explore the measures you can take to help prevent electrostatic damage to your components. To help protect your components from electrostatic discharge, be careful where you touch them. Don't touch electrical components or electronics. For example, when installing this video card, hold it by the bracket. Don't touch the connectors or the circuit board. Doing this increases the chance of damaging the card. When installing the card, if you need to push down on it, do it from either side. Make sure your fingers are pushing down from the top and not touching the components on the circuit board. The same applies to memory modules and other components. Make sure you are not touching the components and don't touch the connectors. This will greatly reduce the chances of components being damaged by static electricity. When handling components with pins, like CPUs, don't touch the pins. Hold the components from the side and avoid any direct contact with the pins. If you touch the pins, you increase the chance of damaging the component. Let's now look at what anti-static equipment is available. Shown here is basic anti-static equipment. If you don't have all of these, don't worry. Most technicians won't have them all. But some anti-static protection is better than none. I will quickly go through each before having a more in-depth look. The anti-static mat provides a material layer between the working surface and the equipment you are working on. It is not designed to stop static electricity, but instead slow down the transfer. In a moment, we will see why. Next, we have the wrist strap. The wrist strap, as the name suggests, goes around your wrist to provide a connection to you. Static electricity needs somewhere to go, so next, there's a strap and/or a grounding cord. This connects you to the mat or the computer depending on which one you use. An anti-static mat may have, but not all do, a grounding plug. This grounding plug will plug into a power point and provide a ground for your anti-static mat. Lastly, you have ESD gloves. Anti-static gloves do provide some more anti-static protection, but you will generally find that not many technicians use them because they make it harder to handle equipment. I will now have a look at each item in more detail. Anti-static mats are available in various forms and colors, so they shouldn't be expected to have a specific color. The blue example is thin and easily foldable, making it convenient for technicians to carry and use on work sites due to its portability. On the other hand, the example green mat, another common variety, is made of thick rubber. While these cannot be folded, they can be rolled up for storage. Mats like these are typically used on workbenches and not moved frequently once put into place. It is important to note that the effectiveness of an anti-static mat isn't determined by its color, but rather by its material and construction. You can also get more decorative ones, like the black anti-static mat. The patterns on them don't matter as long as the mat is made of the right material. It is also possible to get custom-sized anti-static mats to cover your tables. Anti-static mats are designed to slow down the transfer of static electricity. You may find that surprising, as you think they would block static electricity, but this is not the case. The reason for this is static electricity needs to go somewhere. You don't want your device to hold on to it. You rather want to drain it away slowly. Let's have a look at why. Let's consider that I have a metal table and no anti-static mat on it. If my body has a static charge and my finger gets close to the table, a spark will jump between me and the metal table. This fast transfer of electricity causes the spark. This spark is what can damage electrical components and is what you want to prevent. To prevent this, an anti-static mat can be added to the top of the table. When I touch the anti-static mat, not the table, the transfer of static charge is a lot slower. A slow transfer means no spark. Thus, you can see why we use anti-static mats. We're not trying to block static electricity, just manage it better. Anti-static mats will absorb a certain amount of static electricity. Eventually, this charge will dissipate into the air. But there is a better way to deal with any static electricity the mat comes in contact with. Let's have a look. Your anti-static mat or your workbench should be grounded. I will look at how to ground the anti-static mat, but the process is the same for the workbench. First, I need to connect a grounding cable to the anti-static mat. You can see this cable has two connectors. One will go to the anti-static mat, the other to the ground plug that I will look at shortly. To connect the ground cable to the anti-static mat, it is just a matter of pushing the connector down onto the attachment connector. On the other end, a ground plug needs to be plugged into a power point or another source of grounding. In this example, I will use a ground plug. You will notice that the two top prongs are plastic, while the bottom one is metal. The bottom prong is ground, and thus the only one that is connected. I will next plug the ground plug into the power point. Since ground is always connected, there is no need to switch the power point on. The last step is to plug in the anti-static cable. You will notice that it has a particular type of end connector. This particular ground plug is a little longer than the standard ones on the market and therefore will only work on this ground plug. You will find that not all anti-static equipment follows the same standards. If you have a ground plug that follows the standard, you should be able to use the cables that come with most anti-static mats. The ground connector may be connected to an alligator clip. You simply need to pull the alligator clip away to get to the connector. To activate the anti-static mat, I simply plug its cable into the grounding plug, ensuring it's now grounded. If you are using a workbench equipped with a ground cable, the process is similar. The ground cable will be attached to the workbench in some manner, and all you need to do is plug it into either a power outlet or a designated grounding point, depending on the configuration of your workspace. This simple step effectively grounds your work area, providing an added layer of safety against static electricity. Let's now have a look at how you would ground yourself. In order to ground yourself, you can use an anti-static wristband. This is a wristband with a cable attached that grounds you. I have two different cables that can connect to my anti-static wristband. The first cable has the same connector on each end. This connects directly to the anti-static mat. The second cable has one of the same connectors and an alligator clip. This is used to connect to the computer case or to the workbench. We will have a look at when to use each cable. I next need to put on the anti-static wristband. On the back of the wristband is a piece of metal. This needs to be touching your skin, so the strap on the wristband needs to be pulled tight. If it is not touching your skin, it is not making a connection. To attach the wristband to the anti-static mat, it is just a matter of connecting one connector to the wristband and the other connector to the anti-static mat. This will essentially ground you. Make sure the anti-static mat is also grounded. I will now connect the anti-static strap using the alligator clip. To start with, connect the round connector to the anti-static wristband as before. You then want to connect the alligator clip to a metal part of the computer case. As most computer cases are painted nowadays, there may not be any exposed metal parts of the computer case. The paint generally insulates the computer and thus won't make a connection between you and the computer. In this example, I've connected the alligator clip to one of the screws in the computer case. Even though the screw is painted, the paint used on the screws is generally not as thick as the computer case and thus should allow a connection to be made. Don't connect the alligator clip to any of the computer components, as you risk damaging those components if you do that. Only connect it directly to the computer case. If you have any free standoffs on the computer case, these can also be used to attach the alligator clip. As long as it's not painted or only lightly painted and connected directly to the computer case, it can be used. Since the wristband is connected to the computer case now needs to be connected to the anti-static mat. It is just a matter of connecting a ground cable to the mat and the other end to the computer case. If you have limited places to connect the computer case, you can always connect the alligator clips together. Personally, I prefer to connect the anti-static wrist strap directly to the anti-static mat. The alligator clips don't tend to hold the cable in place as well as the round connector, thus it is more likely to come loose. If you have an anti-static workbench, it may have an anti-static ground socket attached to it. Generally, this is at the front to make it easy to get to and is connected to the workbench's ground connection. To use it with the alligator clip, remove the alligator clip and push the connector in. For the round connector, simply connect it by pushing it onto the other connector. This is another way to ground yourself. If you don't have an anti-static wristband, you can always touch the metal contacts to ground yourself. All the methods shown so far are designed to slow down or drain static electricity. Let's look at how you can create a barrier so static electricity can't jump between you and your electronics. Gloves provide a barrier between you and the electronics. They don't stop all electrostatic discharge completely, but they do lessen the risk. As they are a barrier, they do not provide any grounding. They also do not protect against electrocution. They may stop or reduce a small amount of electricity, but they won't stop a high amount. Thus, don't use anti-static gloves for handling mains power. They also do not replace anti-static wristbands or any other anti-static protection, but simply reduce the risk of electrostatic discharge between you and the electronics. The first option I'll discuss is anti-static gloves. While these gloves are a bit costly, they offer the advantage of being reusable. However, they do reduce dexterity, making it more challenging to work with smaller parts and electronics. Using tools with the gloves is manageable, but grasping small items like screws can be difficult. On the plus side, these gloves are designed to allow some air circulation, which helps to reduce sweat buildup, a feature that adds comfort during extended use. There's a range of gloves available on the market, varying in thickness. Generally, thicker gloves offer greater protection against static electricity, but thinner ones offer better dexterity. The next option you have is disposable gloves. These gloves are generally made of 3 different materials. Latex is the cheapest one. Some people have latex allergy that may cause itchy skin and other serious side effects in really bad cases. The next type is vinyl, which won't cause an allergic reaction, but is less puncture resistant than latex. Nitrile gloves are the most expensive out of the 3. However, a box of them should still be cheaper than a pair of reusable static gloves. Nitrile gloves also provide the best anti-static protection, so I would recommend them as the best choice out of the 3. Regardless of which one you choose, they are cheap, disposable, and have less dexterity loss than anti-static gloves. Although you could use gloves whenever you are performing maintenance on computers, The most common use you will find is when working on devices like mobiles. IT technicians tend to swap components in and out of a computer system, which means you don't need to come in close contact with circuits if you are careful. However, since IT includes mobile devices, you may get asked to replace an LCD screen or some other component in a mobile device. Since you are getting close to the circuit boards, small cables, and small parts, the risk of static damage is higher. Hopefully, your company will send the mobile device to a repairer to get it fixed, rather than asking you to do it. That's enough theory. Let's have a look at what are the important takeaways from this video. In the real world, before working on a device, always disconnect the power. Modern computers, when they are off, are essentially in standby mode and are drawing power. If present, make sure the voltage switch is set correctly. If it is set incorrectly, the power supply will most likely blow up if you plug it in and may damage the device. When connecting circuits, don't overload them. In the best case, it will trip a circuit and you may need to reset it. In the worst case, it may be a fire hazard. If you are using a universal power supply and not the one that came with the device, make sure that you match the voltages. Higher voltage will most likely damage the device. Amps need to be equal to or be greater. There is no guarantee a different power supply will work, but depending on your circumstances, it may be worth a try. When it comes to anti-static protection, devices are pretty resistant to anti-static electricity nowadays, but they can still be damaged if they get an electrostatic shock. As a bare minimum, ground yourself before touching electronics. You should do this using an anti-static wristband. If you don't have one, you can always ground yourself by touching a metal part of the computer case. If the case is painted, touch one of the screws, as they generally only have a thin layer of paint on them. If your workbench has a grounding socket installed, you can always touch that to ground yourself. If all else fails, touch anything near you that is grounded. Keep in mind that if you are not wearing an anti-static wristband, you can still accumulate additional static electricity while working. Thus, you may need to keep grounding yourself to prevent accumulating a charge, particularly if you are working in an environment or wearing clothes that accumulate charge very easily. Also, as a bare minimum, handle the components by the edges. Don't touch metal connectors, pins, or components on the circuit board. By grounding yourself and handling electronics with care, you can significantly reduce the risk of accidentally causing electrostatic damage to your devices. If you want to take some more precautions, use an anti-static mat. If you don't have one, don't place components on surfaces that are not friendly to components. If you don't have anything, use the box the component came in. Any anti-static protection is better than none. You can also use gloves to provide a layer between you and the device. In the real world, most IT technicians won't use gloves. They provide some protection, but simply grounding yourself and holding devices by the edge reduces a lot of the risk. You will see gloves used a lot in mobile device repair and when working on devices that have small components. When working on devices like these, since they are so small and the components are so densely packed, it is easy to make a mistake and touch something you shouldn't. Even if you are being very careful, the risk is much greater than swapping out large components like graphics cards. Do not forget that if you are using an anti-static mat or a workbench that is also grounded, you need to clip them to something that is grounded in the case of the mat, or plug them into a power point with a grounding plug in the case of the workbench. That concludes this video from IT Free Training. I hope this video has helped you understand electricity a bit better and how to protect your components and devices when working on them. Until the next video from us, I would like to thank you for watching.